If IV drug use has nothing to do with being HIV positive, out of those 150 people, I'd expect 20% again to be HIV positive. 20% of 150 is how many? 30, right? Everybody agrees 30? Okay, 120. That's my expected values for this table. Okay. Now I'm going to take a quick peek at that PDF file I just showed you. I'm only going to take a quick peek at it because I want to use the same numbers as I used there. Oh, I got the wrong one. Where did I put it now? I could say I must have closed it. Let's see what I used. Okay. Okay, I'm going to go back here. So now, let's say I actually do this study. Okay, and when I actually do this study, what I find is that out of my 50 people that are IV drug users, I find that 15 of them are HIV positive and 35 are not. And among my non-IV drug users, I find that 25 of them are HIV positive and 125 are not. Okay, so there's a difference here, isn't there? This is different than what my expected values were. So now let's think about this for a second. If I were to do a study where there's no relationship between IV drug use and being HIV positive, and I did this study and in a population where this was true, and I sampled 50 people that were drug users, 50 people that were not drug users, would I expect to get exactly 10 and 30 as the result? I mean, would that be practical? Would you really expect that to happen if you did it in real life, even if that were the case? No, right? You'd expect that maybe I get 11, right? Maybe I get 14, maybe I get 8, maybe I get a little higher, a little bit slower. It's just like any sampling, right? We may not get, we're not likely to get exactly what our expected values are. So now, but how are we going to tell if there really is an association between these two? Well, what we're going to look at is not just the fact that there is a difference between our expected values and our actual observed values. We're going to call this observed values, but we're going to look at how big those differences are. In other words, the bigger the differences between our expected values and our observed values, the more likely it is that there is an association between the two, right? If these differences are small, not likely that there's a difference between being a drug user and not being a drug user. If the differences between our expected values and observed values are large, then we think that there likely is going to be a difference. What do you think our null hypothesis is going to be here? Somebody make up a null hypothesis. What did I just use I just used the word about 12 times with an A, right? Association, right? Okay, so what would you say, like in words? What would be a good null hypothesis? Yeah, there's no association. Null means basically none, but no association between IV drug use and HIV status. Okay, what's our alternative hypothesis? There is. Okay, there is an association. Okay, that's our null hypothesis or alternative hypothesis. So now we're going to have to calculate a statistic. Uh-oh. Forgot about that. Okay, we're going to have to calculate a statistic. Come on, come back. There it is. We're going to have to calculate a statistic that will let us figure out what the probability is that we would get these results, that we'd get such a big difference in these results if they were from the same population, if there was no association between IV drug use and non-IV drug use. Okay, we're going to call that statistic chi-square. Okay, now I'm going to recreate these numbers, I hope. I'm going to try anyway on the next page. So I can start with a clean slate, and you can help me out if I get them wrong. Okay, this was 20 and 30 This was, what did I say here? 30 and 120. Is that right? Yeah, what were my expected values there? Excuse me? Oh, 10 and 40. Okay. Hey, come on. 10 and 40. And on the bottom? 30 and 120. I got those right. Okay. And my observed values? Okay. 15 and 35 and 25 and 125. Okay, so I'm going to invent a statistic that I'm going to call chi-square. And chi-square is going to examine each one of these boxes. It's going to compare, let's see, this is IV drug use and no IV drug use. This is HIV positive and HIV negative, right? And the same thing on this in this contingency table. This is expected values. These are my observed values. Okay, so I'm going to invent this chi-square statistic. This chi-square statistic is going to look at each one of these boxes and take a look at the observed value for an IV drug user that's HIV positive, the observed value of and the expected value for an IV drug user and whether or not he's HIV positive. Okay, and I'm going to create a statistic that says, okay, observed value minus the expected value. Okay, what's the difference between the observed value and the expected value? 5. Okay, good. And now I'm also going to do that for, whoops, that back. I'm also going to do that for, let's say, for IV drug user HIV negative, right? I'm going to add that. I'm going to add up the different. I'm going to add all these differences together. So this one happens to be 5. The next one happens to be, let's see, 40 and 35. Well, if this one observed is 15 minus 10, 35 minus 40 is how much? Minus 5. What's happening here has happened before when we tried to do this with sum of squares and stuff like that, right? What's happened is that these are all going to cancel out. It's going to be 0 because one's going to be in another location in that contingency table. So I can't just leave it that way. I'm going to square the differences, right? And so I'm going to say the observed value minus the expected value squared. And again, I'm going to do that for each one of these cells. Okay, observed minus expected squared. Add all of these together. Okay, and when we did that for, hold on a second. Hang on. Am I having? I'm going to show you a second. I just want to get that to go away. There we go. Okay, don't worry about it for a second. These are our observed values, right? These are our observed values. These are our expected values as we calculated them before. Okay, what we're comparing is in the observed values, the person that was the IV drug users, 15 out of 50 were HIV positive. In the expected values, we only expected 10 out of 50 to be positive, right? So for that box right there, for those two boxes right there, this value is equal to 15 minus 10 is 5 squared, right? Plus, I'm going to go to the next box. Next box is 35, right? Minus 40 is negative 5, right? Negative 5 squared. Plus, the next box is 25 minus 30 is negative 5 again, right? And the last box is 125 minus 120, which is plus 5 squared. Everybody comfortable with that? Right? Not anything advanced, not anything super complicated or anything like that. Well, one of the problems here is that it's very nice that I did that, but I artificially inflated these numbers by squaring those differences, right? Remember what we did with sum of squares to take care of that, right? We divided by the actual means in sum of squares. right? So I'm going to divide this by the expected values, right? Down here, it's going to be observed minus expected over the expected values, over the expected value here, over the expected value here, over the expected value here. So this first one, the expected value was 10. This second one, the expected value was 40. This third one, the expected value was 30. And this last one, the expected value was 120. Okay, everybody follow me? Right? Pretty simple so far, right? Okay, and don't worry about it. If you don't remember how to do this, we can lay out little tables with A, B, C, D, and stuff like that. So you can actually literally just follow a formula to fill it in. But nothing very complicated here so far. So now let's actually work this out. 25 over 10 is what? 2.5, right? Okay, plus 25 over 40 is, how much is that? 0.625, is that right? Did I get that right? Okay. 25 over 30, 25 over 30. I'm taking your word for this. I don't have a calculator here handy. 25 over 30. I'm sorry, 0.833. Good. And 25 over 120. 0.2? 0.21. Okay, good. All right. So now let's add all of these together. What do we get if we add them all together? How much is it? How much? 4.168, was it? Well, 4.17, let's call it. That's my value for chi-square. If there's a big difference between my observed and my expected values, would I expect this number to be bigger or smaller? The bigger the difference between the two tables, the bigger that number is going to be because it's based on the differences between each cell in the two contingency tables, right? So now what we have to do, we have to figure out, well, what does a chi-square of 4.17 mean to me? Well, I know the bigger that number is, the bigger the difference between between the expected values and the observed values, and the more likely that it is that the observed population and my expected population are not the same. That I can say that there's a difference between HIV use and IV drug use and HIV status, that they are associated in some way. Okay, so now where am I going to go to find out whether or not these things are associated? Well, just like everything else, we have a table. We have a statistical table that gives us values for chi-square, probabilities for chi-square values of a certain size. Well, we don't always have a 2 by 2 table, do we? Sometimes we can have three values, like we could have IV. We could have a person that uses IV drug use regularly, someone that's ever used IV drugs, or someone that's not an IV drug user. So we could have had 3 rows and a 3 by 2 table. Instead, we could have a 3 by 5 table. We could have a 7 by 11 table. We could have a whole number of different tables. Each different kind of tables has an assigned set of degrees of freedom. Okay, the way we calculate degrees of freedom in this case is we take the number of rows minus 1 times the number of columns minus 1. Okay, how many rows we have here? 2. So 2 minus 1 is 1. Columns, 2, right? So this is 1 times 1 is 1 degree of freedom. Okay, so we're going to go to a table. The number of degrees of freedom when we're looking at contingency tables is the number of rows minus 1 times the number of columns minus 1. Okay, rows minus 1 times columns minus. I can't really. I see what's on my screen here. Sometimes if it gets blocked up there, you got to warn me and alert me so that I know to move things around a little. Okay, number of rows. So it's 2 minus 1 is 1. 2 columns minus 1 is 1. 1 times 1 is 1. So it's 1 degree of freedom. Had it been a 3 by 5 table, right? 3 rows and 5 columns, it would have been 2 times 4 or 8 degrees of freedom, right? Rows minus 1 times columns minus 1. Okay, so that's the way we're going to get our degrees of freedom. Now, I'm going to pull that PDF file up again because I think maybe on that PDF file, I have, I'm going to have to open it again. On the last couple of sheets of that, I may have given you, nope, not on this one. Okay, let me go to the next one. Let's see. Okay, where's my chi-square table? Well, before I go to that table, I want to show you a quick picture. Not that picture. That's a nasty picture. I'm going to show you this picture instead. Okay, these curves, remember we're working with a normal distribution? And our tables, our t tables, our z tables for a normal distribution were based on something that looked like a bell curve for the most part. Well, chi-square distribution looks a little bit different. Chi-square distribution is kind of skewed to the right. Okay, for 1 degree, this first one, this blue one, represents 1 degree of freedom, or a low number of degrees of freedom. Okay, and if you look at this, the height is the probability. These numbers on the bottom are the value of chi-square. So what happens is that in the beginning, if we're looking at a distribution where if we're looking at a population where the expected values, the observed value are very similar, then chi-square is going to be a very low number. So we're going to be somewhere around here on this distribution. As it gets bigger and bigger, we're further and further out on this distribution. This is all the possible values for chi-square for there being no association between the two variables, between drug use and HIV status. Okay, so what we want is we want to get a chi-square value that's so far out to the right that there's less than 5% chance of getting that if there were an association between the two of them. So we want to get so far out, there's only 5% left in the right-hand side of that curve. Just like we use when we're doing a t-test or a z, we're comparing z-scores, we're looking to be so far away from the mean that there's only like a 2.5% chance on either side. In this case, it kind of looks like a one-tailed test, right? Because we're only looking at putting all that 5% in one tail. We're just looking at it being very large. You're going to notice SPSS calls it a two-tailed test for the moment that we're going to ignore that. Okay, so I'm going to go over here and I need to get a table that tells me what these probabilities are. So I'm going to look that up here, chi-square table. See if I can't find it here. Chi-square. I know I got one here. Where did I see it? Let me see, I got it over here somewhere. Give me a moment and I'll find it. Is on the same PDF file? Let me see. Yeah, I was just going to go over there and take a quick look to see how things are going there. Page 27. They must be looking at the other one. These are not numbered. Are they looking at this PDF file? Oh, wait. Here we go. Okay, here we go. Here's what a chi-square table looks like. Thank you very much, guys online. And you for letting me know. Okay, page 27. Yeah, mine are not numbers for some reason. Okay, so let's take a look at our chi-square values. This is a typical chi-square table. I don't know if this came from your textbook or not. I don't remember. But at any rate, let's take a look at this. For 1 degree of freedom, right? If we want 5% chance, we want an area of 5% to be the right of this critical value for chi-square. In other words, to have only 5%, to have a chi-square value that's so high that only 5% is left in this distribution of possible outcomes if there is no association, we need to exceed a certain value for chi-square. Well, for 1 degree of freedom, the value that we have to exceed is 3.841. Anybody remember what we called that when we were talking about t-scores? The number we had to exceed for the t-score? Critical value, right, exactly. So we need to exceed that for 1 degree of freedom for us to reject our null hypothesis and accept our alternative hypothesis. So going back to our example, can we reject our null hypothesis? Do we exceed that critical value? We do. Okay, so we reject our null hypothesis. I'm going to throw a quick curve in here. Okay, there's a couple of rules about using chi-square. One of the rules is that all of the values, 25, no more than 20% of the values that's in your expected values can have a value less than 5, and none of your, I think it's none of your observed values can have a value less than 5, and none of your expected values can have a value less than 1, I believe. I'll check that. Okay. In any case, those are a couple of rules. And as far as, obviously, if you're in a situation where you don't have a big enough sample and the numbers are very small, well, we have some limitations, right? So now another limitation is that a 2x2 table, we kind of give ourselves a little bit of extra license that we really don't deserve when we use chi-square. So there's something called the Yates correction. And the Yates correction involves, it's called a continuity correction also. What it does is it tells you to take each one of these calculations that you made, like that 2.5 that you made down here. Let me get this so I can point it out. Okay, that 2.5. It says that you subtract minus 0.5 from that value, and minus 0.5 from, minus 0.5 from your 25, and minus 0.5 from this 25, and minus 0.5 from this 25, and so on and so forth before you actually do the calculation. What that gives you is a slightly different number for chi-square. I'm not going to bother to calculate it here because it's the same calculation, just a little bit more math. When we use SPSS, you'll actually get alternative answers, one with the Yates correction, one without the Yates correction. You can make up your mind which one you want to use. But I'm not going to worry about that for our purposes now. Okay, so now I'm going to move on to a different kind of calculation. Okay, and I'm going to use kind of a similar situation. In fact, I'm going to use the same example. I'm not sure what I used before, but I'm going to use the same example here. Okay. I'm going to redraw my observed values. Okay, here's IV drug use, yes. And IV drug use, no. And I'm going to take a look at HIV status. These are my actual observed values now I'm looking at. This is HIV positive, HIV negative. Okay, so now, what were my numbers again? My numbers were 15 and 35, right, out of 50 people that were randomly sampled, and 30 and 120 out of 150 people that were randomly sampled. Did I get that right? 25. Oh, you're right. Okay, 25 and 125. My actual observed values. Okay, so now out of 50 people, 15 were HIV positive, right? So if based on what we see here, what would you say your risk of being HIV positive if you're an IV drug user? Okay, it's going to be 15 over 50, right? Out of 50 people, 15 were IV drug users, so it's going to be 0.3%, 0.3, 30%, or 0.3, probability of 0.3. Okay, if you're not an IV drug user, what's your risk of being HIV positive in this population? 25 out of 150. So what's that percentage? 1 out of 6. What's 1 out of 6? What is it? 1. What is it? 1 out of 6 is 6, and 4 is 1666, 167. Okay. Yes. What's that? Oh, because hang on, you're getting ahead of me here. The risk is 25 out of 150 people. In other words, what's the prevalence? This is kind of the same thing as the prevalence for that group, right? So 25 out of 150 people, 25 of them are HIV positive. So if I'm doing this because I want to know what basically what the risk is or prevalence is for that particular group. Okay, so I want to be able to use this. If you tell me 100 people, right? If you just gave me 100 people, I could say I'd expect about 17 of them to be HIV positive if they didn't use IV drugs. Out of 100 people, I'd expect 30 of them to be positive if they did use IV drugs. So the risk represents the prevalence or the probability that any individual in that population would have that. That's why I use the 50, the total, instead of the 35. Okay, so now a handy way for me to express this. Obviously, the risk is greater for IV drug users than it is for non-IV drug users. So I'm going to invent another term now called relative risk. Okay, sometimes you call that risk ratio. The relative risk is going to be equal to the risk for IV drug users over the risk for people that don't use IV drugs. Okay, what's that going to be? That's going to be 0.30 over 1.67. Okay, I'm going to take my calculator out because I'm tired of waiting for you guys. 0.3 divided by 0.16, yeah, 0.167. I got the decimal place wrong. I'll correct that. Okay, I'm going to call it 1.8. Okay, that's equal to 1.8, 0.167. 1.8. You're 1.8 times as likely to be HIV positive if you're an IV drug user in this population than if you're not an IV drug user. How useful is that? It gives you an idea of what the relative risk is for exposure versus non-exposure. If you're a smoker, if you're a smoker, you're 9 times as likely to get lung cancer. If you're exposed to asbestos, you're 5 times as likely to get lung cancer. If you smoke and you're exposed to asbestos, your risk is increased. You're 45 times as likely to get. So it's a number you can get your head around, right, to express how much the risk is increased. Okay, so that's relative risk, right? Pretty useful way of describing how much the increase in risk is. Now, let me ask you something. If there were no difference between IV drug use and non-IV drug use in terms of being HIV positive, what would the relative risk be equal to? Not zero, close, got the right idea. It'd be equal to 1. It'd be the same. The risk for IV drug users, the risk for IV non-drug users would be the same number, the same proportion. Same as our expected values. The relative risk, if there's no difference, is going to be equal to 1, right? So now the relative risk I just calculated was equal to 1.8. Can I say that there is a difference? Can I? How do I know that? How do I know it's just not a statistical thing? It's not just sampling issue, right? That like how do I know that I can say with 95% certainty or 5% chance of being wrong? I can't just say that they're different because they're different, right? I have to be able to express what the probability is that they're different. So how do you think I might compare these instead of using like chi-square looking to a table? How do you think I might compare these in terms of probability? Well, let's think about it. Relative risk is 1. I know the relative risk. Relative risk is no association is 1. The one I calculate is 1.8, but it's 1.8 for this population. Just as if I took a sample of 100 people and their average weight was 180, I don't know what the population's average weight is. What can I do to predict what the average weight might be for that entire population? What do I do there? I calculate a confidence interval, right? So we need to calculate a confidence interval. I keep moving this over. We need to calculate a confidence interval for this 1.8, right? Let's say that this confidence interval comes out to be 1.1 to 2.8. Would you say you can reject the null hypothesis? That if you're 95% sure the real relative risk is between 1.1 and 2.8, can you reject the null hypothesis? I see people shaking their head no. It's different. You're 95% sure it's different than what? 1. So you can reject the null hypothesis. Of course, you're 95% certain that the true relative risk is different than 1. Remember, if there's no association, the relative risk is 1. So if the relative risk turned out to be 0.08, excuse me, zero point 0.8 to 3.1, could you reject the null hypothesis now? No, you couldn't, because it's right, because you can't say with 95% certainty that it's different than 1. Okay, anybody got any ideas how you might calculate a relative risk here? We're not going to do it because I don't want to scare you. Run screaming from the room. I know. It's a proportion. Excuse me? No. Actually, think about this. These are all proportions, right? This 0.30 is a proportion. You have a proportion. You have a sample size. You have another proportion. You have a sample size. You basically have two proportions. You can figure out the confidence intervals for each one of these things, right? So you would look at these as proportions, right? But we're not going to do that. We're going to leave that up to SPSS to calculate the confidence interval for us. Okay? So now, you mentioned something before about why don't I put it over 125 instead of 25? You were ahead of me. You were literally ahead of me. I'm going to take another look at this same data another way. Okay? I'm going to redraw this. Okay, and I'm going to I got the box wrong every time so far. Why not this time also? Okay, let me see. 15, 35, 50. Wait, don't tell me. 25, 125, and 150. I got to write this time, right? Okay, this HIV positive, this HIV negative. This is IV drug user, IV non-drug user. Okay, now she mentioned, well, gee, why instead of taking 15 and put it over 50, why don't we take 15 and put it over 35? In other words, HIV positive versus over HIV negative. Okay, so you want to know something? That's called odds. And I'm gonna diverge for a second and talk about horse racing. Can you see that? What's that? Oh, I'm sorry. You're 150. Okay, 150. Okay. Okay. Let's talk about horse races. Let's talk about horse races. When you go to the track and you look at the what is that called again? The board. What is that board called? What's that? The tote board. Tote board. I'm making this up. I know exactly what it is. I go to the track occasionally. When you look at the tote board and you see something like odds 2-1, what does that mean? That means that if this race were run 3 times, they're predicting that 2 times the horse would lose and 1 time the horse would win. If it's 15-1, they're predicting that if that race was run 15 times, that 15 times this horse would lose and 1 time it would win. Right? Isn't that kind of just like, in this case, if we're looking at odds, if this took place, if we measured this 50 times, 15 times we'd find a person that was HIV positive, and 35 times we'd find a person that was HIV negative. So our odds for someone that's an IV drug user, the odds of having HIV are 15/35. A little bit different, right? A little bit of a twist. Yes. I lost. Oh no. I'm gonna. When I get a chance here, if I get a chance, I'm gonna tell it to turn off the screensaver on that thing. Okay. So, what's the odds of being IV negative? If you're not an IV drug user, what's the odds of being HIV positive? Yeah. What are the odds? It's 15/35 if you're a drug user. If you're not a drug user, it's 25/125. Okay, let's resolve those. What are those? Excuse me? What is this one? You have to have the right answer because you maybe stop using my calculator here. I'm going to use my calculator because I can't hear you. You know, you whisper, and even if you got the right answer, I can't hear you. Let me get this one myself. This first one. Since I started it, I'm going to call it 0.43. Okay, 0.43. And what was the other one? It's 1/5, right? 0.2. Okay. So now, what do you think I'm going to do next? To measure what's the relative odds. What's that going to be? It's going to be called my odds ratio, right? Anytime you say ratio in statistics, you mean you're going to divide one thing by another, right? Okay, dead giveaway. 0.43 over 0.20. Okay, what's that come out to? Comes out to 2.15? 2.15? 2.14? Okay, I'll take your word for it. 2.14. Okay, the odds are 2.14 times as great that you would be HIV positive if you're an IV drug user versus if you're not an IV drug user. Is that the same as we got for relative risk? No. See, now as a non-statistician, just in my head, I always feel more comfortable with relative risk than with odds ratio. But guess what statisticians use 90% of the time? Odds ratio. Most of the studies that you're going to see, they use odds ratio rather than relative risk. There are reasons for that. But just intuitively, I feel more comfortable with relative risk because it's a little thing, you know, people are not statisticians. I think it's a little bit easier an idea to wrap your head around. Okay, but odds ratio is used more often than relative risk in most studies. Well, you can use either one. So now, how do I know? Yes, 2.14 times as likely. Your odds are 2.14 times as great of being HIV positive if you're a drug user than if you're not an IV drug user. Okay. So now, again, how do I know whether that's significant enough for me to say that there's an association between IV drug use and non-IV drug use? In other words, reject my null hypothesis that there is an association. Say there is. How do I do that? What do I need to know? I need to know my 95% confidence interval. Because if the odds are the same for IV drug users and for non-IV drug users, what's our expectation the odds ratio is going to be? 1, right. So this is 2.14. We need to know our confidence interval. Again, these are proportions. You can calculate a confidence interval if we wanted to do it this way, the hard way, mathematically. But we're sticking with fairly simple math for now. And we're going to let SPSS do the heavy lifting. Okay, so now we're going to take a 5-minute break. Okay, I'm going to get SPSS up and running on my computer. We're going to get our heads around. I get the data set up. There's 2 files that you might want to download. One is called from Blackboard Stenosis, and the other one is called, I think, just NYC survey or something like that. There's 2 files, 2 SPSS files that I uploaded that you might want to download both of them. Okay, let me just, I also want to take a short break because I want to check to see if these guys online are still online and if they have any problems. How are you guys doing online? No response. Okay, great. Okay, good. They're following it. Good. I'm glad to hear that. Okay, I'm going to move this out of the way. I'm going to open up those files myself. Yeah, it's NYC data, reduced set. Okay.